In single variable calculus, you learn the product rule, the quotient rule, and the most important of these, the one rule to rule them all, was the chain rule. And if you have the chain rule, then you actually have the product rule and the quotient rule and all these other rules for differentiation. So the chain rule is the most powerful rule for computing interesting derivatives. It gives you a very simplified way to compute things. And so we need a chain rule in order to do multivariable calculus. But what is this chain rule going to look like? Well, first of all, suppose we have this function. Suppose we have a parametric curve. So suppose x of t, and let's use a very concrete example, this spiral curve that we saw from last time, cosine of 2 pi t, t sine of 2 pi t. And let's say we have f of x1, x2 equal to x1 squared plus x2 squared. So what does this do? This is the length squared of x1, x2 coordinates. That's what f gives us. Well, we can compose these, just like we have seen that we can compose multivariable functions. And when we compose these, we get f of x of t, so it's a function parameterized by t, is equal to, when we plug in t cosine squared 2 pi into x1 and t sine squared sine 2 pi t into x2, we get t cosine of 2 pi t square plus t sine 2 pi t square. And this guy is going to be equal to, we're going to have a t squared that we'll be able to factor out, t squared times cosine squared of 2 pi t. So I'm skipping just a couple of steps, but this should be, you should think about this if it's not immediately clear. You should work this out on your own. And of course, cosine squared plus sine squared is going to give us just 1, and so we obtain t squared. So this now is a function from R1 into R1. And we know how to differentiate that. So the derivative of this function, d dt of f, almost drew an arrow over it, f of xt is going to be equal to, well, it's just the derivative of t squared, and we know what that is, 2t. Our chain rule, if we write it, has to recover this. In order to motivate the chain rule, we're going to use our linear approximation. We know that, so I'm just going to do a linear approximation for a two-dimensional thing. So I've got f of x1 plus the differential of x1, x2 plus the differential, and you can think of this differential as just delta. It's just an infinitesimal quantity that we're changing x1 or x2 by. Remember that this is well approximated by f of x1, x2 plus partial derivative df dx1 evaluated at x1, x2 dx1 plus df dx2 of x1, x2 dx2. Well, that's really nice, but now we've got this as a function of t, x1 plus dx1 here. We would normally have that, but our x is a function of t, so we write, instead, we've got x1 of t plus dt, the differential with respect to t. This is going to take the place of x1 plus a little change. Similarly, and we shouldn't have an arrow there, x2 of t plus dt here is going to take that change. And what happens when we have a single variable function that we're changing by x1? Well, this is well approximated by x1 of t plus dx1 dt at t times my differential of t. And similarly, this is well approximated by x2 of t plus dx2 dt evaluated at t dt. Now that we have this expression, we know that my differential dx1 is actually dx1 over dt evaluated at t times the differential of t, so an infinitesimal change in dt. That means that I'm just going to substitute this term in for my dx1, and this term right here, will go into my dx2. And how does this change? How does it now look like? Well, we've got f of x1, so now everything is a function of t, so I've got x1 at t at some time t, x2 at some time t, plus I've still got df dx1 here. I don't substitute into that, I'm just substituting into differentials, right? And I've got x1 of t, x2 of t. And now my dx1 is this, that's dx1. So I multiply by dx1 over dt of t dt. Plus, now that second term is df dx2. This doesn't change because it doesn't depend on the differential quantity. And I have dx2 now, dt of t dt. But now I have two terms that are dependent upon dt, and so I can factor. What do I get when I factor? Finally, when I factor, I get f of x1 at t, x2 at t, plus this term here. I've got df dx1, x1 of t, x2 of t, times dx1 dt of t, plus partial with respect to f of x2, x1 of t. I'm going to run out of room here, so I'll write it on the second line here. So df dx2 of x1 of t, x2 of t, not a partial. Don't write it curly when it's supposed to be normal, when it's supposed to be Roman instead of Greek. And then I have a dt term here that I draw out. So this, right, if I have a one-dimensional function, say g of t plus dt, right, it's well approximated by g of t plus dg dt of t dt. And so this is my analog of the derivative with respect to t. And this is what gives me my chain rule. Let's verify that it works for this function. We know the function above had a derivative of 2t. So let's use our chain rule. Right? So this is the chain rule. So I'll write it out explicitly for our situation. So we've got df of x of t over dt. That was a really bad line there. Particularly bad line. So the chain rule is this. It says I take derivative of f with respect to the first term, x1 of t, x2 of t, normal derivative of x1 with respect to t of t, plus df dx2 of x1 of t, x2 of t. Now dx2 dt of t. Now there are a lot of symbols being thrown around here, so this is getting really confusing, right? It's going to be a little confusing at first, which is why you probably need to go back through this video a couple of times until it really sinks in what exactly is going on here. But this is our rule. This is our chain rule. So you could just memorize this for 2, and we'll talk about what the n-dimensional one looks like. I mean, we just tack on a bunch of other terms just like this. It's not too crazy. But if we compute this, then we'll get, if you compute the derivative of f with respect to x1 and evaluate it here, you're going to get 2x1 of t. Because remember that f is x1 squared plus x2 squared, so I get that. If I take the derivative of x1 with respect to t, I'm going to get cosine of 2 pi t minus 2 pi t sine of 2 pi t. The term I get from this is going to be plus now 2x2 of t. Remember, the function was symmetric in the x1 and x2 variables, so this happened. Times, and remember, we already took this derivative before, if you'll remember, sine of 2 pi t plus 2 pi t cosine of 2 pi t. When we work that out, we plug in this term, we plug in this term. What we'll end up with is 2t. So I want you to work through this on your own. Cosine squared of 2 pi t plus sine squared of 2 pi t. And of course this term, again, cancels out the 1, and I get 2t. Which verifies the chain rule, at least for this case. This chain rule worked out. But it's a theorem that this actually works. The chain rule is always a theorem. In order to state this theorem, we need the idea of being a C1 function. So definition, we have that f from Rn into R1 is C1, that's the definition, if, so basically you would read this, its first derivative is continuous at x naught, so its first derivative is continuous at x naught, if, and that's a vector in Rn, if we have that, there is a small ball around x naught such that this derivative, so this actually should be, say, R1 to R1, and this will just be x naught. So a small ball in this case is an interval. So a comma b with x naught in AB, such that f prime is continuous on AB. That is, there are no jumps at this point. And so theorem, suppose x of t equals a bunch of the coordinate functions, has C1 coordinate functions, at a point t naught. So we fix a point t naught, and we ask that the derivative is continuous near t naught for each of the coordinate functions. And f from Rn into R1 is C1 around x of t naught So actually we can ask for the derivative there, right, to be continuous around this guy. Then, or so this means that all the partial derivatives are continuous around this guy. The composite function g of t equals f of xt is c1 around t naught. That is, it has a continuous derivative around t naught. This is a r1 to r1 function, and dg dt of t naught is equal to, and this is the chain rule, partial with respect to x1, x evaluated at t naught, x1 prime, so derivative of the first coordinate function evaluated at t naught, plus df dx2 now. Still I plug in the same point. Now it's x2 prime of t naught, plus, and we do this for all n coordinates, df dxn of x of t naught, xn prime of t naught. And this is the first chain rule, but we'll have many others.